Okay, come on, come on, come on. That's right. Cheer up. All right, all right. Let's dive into Chapter 1, Lecture 4, Atomic Structure. So, talked a bit about atoms. Let's talk about Dalton. Well, continue from Dalton, excuse me. So, Dalton didn't identify how atoms of an element are the same or how they are different. He didn't really need to. I mean, a theory is better the more complete it is, but it was good enough as it was. But later work in that same century, starting in the same century, uh, showed that atoms are divisible and have internal structure. This was when we started correcting Dalton's theory. Okay, so first up, God damn it, hold up, adjusting the mic. First up, we have J.J. Thomson in the 1890s. Let me close my door real quick. Love the puppy, but I'm going to have to keep him out. All right. So, J.J. Thomson in the 1890s, who did experiments with cathode ray tubes. Then came R.A. Millikan in 1908, around there, did his oil drop experiment. And Ernest Rutherford, who did the gold foil experiment, also in the early 20th century. Okay. So we're going to talk about these guys in more detail. Never fear. Thomson is the one who discovered the electron. Millikan is the one who weighed the electron. Rutherford discovered the nucleus. So, Thomson. Up here in the top right, we have a cathode ray tube. So, cathode as opposed to anode. What he did was he hooked up one of those brand new fancy batteries to this empty glass tube. I say empty because it is almost, but not quite, a vacuum. Over here on the left, we have the cathode. Over here on the right, we have an anode. So he created this electric charge, this buildup of charge. Eventually, that charge would get strong enough that you would get this beam through the mostly empty tube. Because you have a tube, and you have a cathode, and you have a ray passing through this tube. It's called a cathode ray tube. People were interested in what that ray was. So, Thomson spent some time playing around with it. He got really fancy with his tube. And you can see right here in the middle of the tube, he set up another electric field, a pair of plates. And he attached a different battery to that. So negative on one side, positive on the other. And he saw that this deflected the ray. So even though it was this beam of light, it was not, in fact, made of light. Light doesn't respond to electric fields. If it did, we could see electric fields. We can't, so we know it doesn't. So he knew that this wasn't light. Instead, he knew that it was a beam of particles that were creating light in the very thin atmosphere inside the tube. Now, the thing is, they knew something about how electricity and magnetism worked. So he was able to measure how much this beam was displaced. He was able to measure not the charge and not the mass. Instead, he was able to find the ratio of the charge and the mass. Okay? Because the stronger the charge on the particle, the more it would be deflected. The higher the mass of the particle, the less it would be deflected. So he wasn't able to determine either one independently, but he was able to determine the ratio between them. And the best he could do was that this particle, this unknown particle, whatever it was incredibly small, much, much smaller than the hydrogen atom. And at this point, they had already been measuring the masses of atoms for quite some time. They knew the mass of the hydrogen atom, and they knew that it was the smallest possible atom. So, in other words, Thomson had confirmed the discovery of subatomic particles. That is to say, particles, pieces of matter, that are smaller than the smallest atoms, and in fact are the constituent components of atoms. So this was the first big change to Dalton's theory. Atoms are not this undifferentiated mass, they can be subdivided. So, big question, if atoms can be subdivided, if they have particles that make them up, how are those particles put together? What is the internal structure of the atom? What Thomson proposed was what is now called the plum pudding model. You'll see that down here in the lower right. Plum pudding it's pudding with plums in it. So plums are just little fruits, you know. So they thought that you had this pudding of positive charge with these negative electrons studded in it. Okay. That was the particle that he had discovered. I don't know if I mentioned that. He discovered the electron. He called it the corpuscle at first because he's boring and stupid. But this is what he proposed. It turned out to be entirely wrong, but hey, it's decent for a first start. Next up, we have Millikan, the next name you're going to have to remember in this section. Millikan devised this experimental setup over here on the right. You have a vacuum chamber with an atomizer. Okay, this is just a bottle of oil inside of, go ahead and call it, it's a perfume vial, you know. And an atomizer is just a thing that will send out a very, very fine mist, okay, just like a perfume bottle. So pss, pss, he did little spritzes of oil into this container. So you get these very, very small droplets of oil. Then you have this charged metal plate with a very small hole in it. The hole is shown rather big here in the picture, but it was much, much smaller. The point was to limit the size of the oil droplets. And then, right here, he has this source of X-rays. It's meant to be an ionizing radiation. That is to say, it strips electrons off of the oil droplets in order to give them a charge. Okay? So by stripping the oil droplets off of it, it gives it a negative charge. But those electrons have to go somewhere. Some of them end up with positive charge. Some of them end up with negative charge. Then he has a microscope in here so he can actually look at and measure the size of those oil droplets. And then he has another metal plate down at the bottom with a negative charge. You always have to have a positive and a negative when it comes to electricity. So when these oil droplets got to the bottom of the chamber, some of them would have negative charge, and bada boom, they would be repelled by this metal plate, and they would be suspended. They would float, because like charges repel. So knowing the size of the droplet, he would know the mass of the droplet, because he was able to measure the density of the oil. And thus, and he was also able to control the charge on the plate, so he would know the size of the charge on the droplet. And thus he was able to measure not only the charge, but also the mass of the electron. Okay? So that is what this experiment was for, to strip electrons off of these oil droplets. Now, he didn't have perfect control. He wasn't able to strip individual electrons off there. But when he measured the charge, it always came up as a ratio of a particular number. And that number was the charge of the electron. It was either 1 electron or 2 electrons or 3 electrons. And thus he was able to get the charge of the electron. Okay? And because Thomson had found the ratio between the charge and the mass, that meant that once Millikan had the charge of the electron, he also had the mass of the electron. And he found that they were both incredibly small. He confirmed that Thomson was correct, that the electron was much very smaller than the hydrogen atom. So Thomson finds the electron, proposes the plum pudding model. Then we get Millikan who finds the mass and the charge on the electron. Found that the mass was 9.11 times 10 to the negative let's see, I believe it is 31 kilograms, and the charge, the symbol for charge is often Q, was negative 1.602 times 10 to the negative 19 coulombs. Capital C means coulomb, and that is the unit of charge. So both of those numbers, incredibly small, very, very small. Okay. Next up, we have Rutherford, Ernest Rutherford. He did the gold foil experiment. Oops, let's go ahead and clear off that guy. All right. So here's Rutherford's gold foil experiment. Here we have a little chunk of uranium inside of a block of lead. Uranium is naturally radioactive, and it releases what are known as alpha particles. An alpha particle, let me go ahead and bring this back up. So this is going to be Rutherford. An alpha particle. When they were, discovering and naming little bits and pieces of radiation, they had alpha particles, beta particles, and gamma radiation. Those are just the Greek letters A, B, and C. So alpha particle is, we now know, a helium nucleus. 2 protons and 2 neutrons. Okay, so just this little chunk of very massive, massive compared to electrons. It's still the second lightest element in the universe, with a positive charge. Okay? They didn't know it was a helium nucleus back then. Now we do know that. Okay? So that is what this little blob of uranium was firing at. Let's go ahead and bring this up. Okay, nobody's in the chat. Okay, I didn't think anyone would be. That's what this little chunk of uranium just fires out at random. But it fires it out in all directions, and not particularly dangerous, not incredibly safe either. So he took that little chunk of uranium and he embedded it in a block of lead with a very narrow hole drilled in it. So instead of firing alpha particles out in all directions, it can only fire them out in one direction. He made a very small gun that never stopped firing alpha particles. Then he aimed it at this sheet of gold foil. So the reason he did that was because he said, okay, we know the alpha particle is about the same size as an atom. Why not fire it at atoms and see if it has an impact? See if we can investigate the internal structure of materials. This was a really good idea. This is more or less exactly how we look at stuff today, except instead of firing alpha particles, we just fire neutrons or electrons. A little bit easier to control, a little bit better results. The reason he used gold foil is because gold is expensive, and people had gotten really, really, really good at hammering gold out into incredibly, ridiculously, absurdly thin sheets. So this was basically the thinnest material he could find. So his idea was we fire this at this incredibly thin material, it'll interact with as few layers of the gold as possible. It'll make it through, it'll be deflected by the gold atoms inside there, and we'll see how those atoms are arranged in the gold foil. Really good idea, exactly correct. But his results were incredibly surprising because the overwhelming majority, like 99% of the alpha particles, went straight through the gold as if it wasn't even there. This was surprising because gold is a very heavy element. Let's go ahead and bring up, oops, there we go. Let's go ahead and bring up our periodic table. ptable.com, here's gold. Okay, 197 atomic weight. Compared to helium with 4, or hydrogen with 1. So gold is fairly heavy. He was expecting to find some sort of result. He wasn't necessarily expecting no result. He wasn't expecting most of them to go straight through as if the gold wasn't even there. But even more surprising than that, some of them deviated slightly as if they'd interacted with something. Some of them deviated a bit. Some of them bounced off the gold foil almost, straight backwards. Or they went radically sideways. The reason he was able to see this is because of what's known as a scintillation screen. It's just something that bing would give off a little brief glow um, uh, in response to being struck by an alpha particle. So, uh, in essence, he had fired bullets at a wall, expecting most of the bullets to go through, but to interact with the wall. Sort of like if you fired a gun inside your house and it went through the drywall inside your home. Instead, he fired them at the wall and they passed through like there was no wall. Except that some of them bounced back like the wall was made of Superman. I mean, it was just, this incredibly ridiculous result. But Rutherford was a clever dude. He knew how to interpret this, and he came up with the Rutherford model. Most of the matter of the atom is packed into this incredibly small, incredibly dense nucleus, where almost all of the mass of the atom is contained. He knew it was incredibly massive because of the way the alpha particles bounced off of it, like it was just incredibly massive. He also knew that it was incredibly small because of the way most of the alpha particles went right by it like it wasn't even there. He knew most of the atom was empty space, in other words. Okay? So this incredibly small, incredibly dense nucleus. He also knew that the nucleus had to have the positive charge of the atom because the alpha particles bounced off of it. Alpha particles have positive charge, so the nucleus has to have positive charge. The alpha particles went straight through the empty space because that's where you have the negative charge of the electrons. So this experiment just completely got rid of the plum pudding model, instead replaced it with the Rutherford model. It confirmed two things. First off, it confirmed the existence of protons, positively charged particles, and that those protons are located in the nucleus. This also led to a couple of other things. First off, neutrons. Okay? Protons have positive charge, like charges repel. Why aren't the protons exploding apart from one another with incredible velocity? They're packed into this incredibly dense space. They should not want to be that close to each other. There must be some sort of glue holding the nucleus together. And that glue isn't canceling out the positive charge of the nucleus. Therefore, it has to have a neutral charge, therefore, the neutron. The other thing it did was it threw a complete wrench into our understanding of the universe, because according to physics, this cannot possibly exist. So this is where things stood after those three experiments. The structure of the atom. We know that there are 3 subatomic particles located in 2 regions. Almost all of the mass of the atom is located inside of an incredibly small nucleus. Almost all of the volume of the atom is made up of a very, very low mass cloud of electrons outside the nucleus. Okay? So inside the nucleus we have protons and neutrons, which are very massive particles, about 1,000 times more massive than electrons, or actually, in fact, about 1,800 times more massive than electrons. You don't have to memorize the masses of these things. Those numbers are a little bit too wonky for that. So the proton, 1.672622 times 10 to the negative 24th grams. Neutrons are just slightly heavier, 1.674927 times 10 to the negative 24th grams. And electrons a lot smaller, 9.109383 times 10 to the negative 28 grams. So 1,800 times smaller. Instead of talking about them in terms of mass, we often talk about them in terms of atomic mass. Okay? So a proton has an atomic mass of just over 1 atomic mass units. A neutron has an atomic mass slightly heavier than a proton, and an electron much, much smaller. And then in terms of charge, a proton has a positive 1 charge, a neutron has a 0 charge, and an electron has a negative 1 charge. Nice and symmetrical. Again, these are units of these subatomic particles. in terms of the stuff that we work with in physics, in terms of coulombs, it's positive 1.602 times 10 to the negative 19th and negative 1.602 times 10 to the negative 19th. But it's not particularly convenient to work in coulombs when you're looking at subatomic particles. So we don't. Instead, we just say positive and negative. So protons, very, very massive. They carry the positive charge. They're located in the nucleus. And the role of the proton is to give the atom its identity. We'll get to that in a bit when we talk a bit about the periodic table. Next up, we have electrons. They're tiny. They have negative charge. They're located outside the nucleus. The number of electrons gives the atom its personality. Neutrons are also massive. They're heavy. They have no charge. They act as nuclear glue. And the number of neutrons will give an atom its flavor. Okay? The number of neutrons can change. It doesn't have a huge impact on chemistry. But it does give us what are known as isotopes. Okay? So one of the ways that Dalton was wrong, we now know, is that every atom comes in multiple varieties called isotopes. Okay? So every atom of an element has the same number of protons. That is what he got correct. They're all the same in that they have the same number of protons. So we go back to our periodic table. Every atom of hydrogen has 1 proton. Every atom of helium has 2 protons. Every atom of iron has 26 protons. Every atom of gold, 79 protons. That's what I meant when I said that the number of atoms gives the element its identity. Or sorry, the number of protons gives the element its identity. Okay? But the different isotopes have different numbers of neutrons. So for example, hydrogen has 3 naturally occurring isotopes. And these are the only isotopes that have names. So the first isotope, the overwhelming majority of the hydrogen in the universe, is protium. 1 proton, 0 neutrons. It's just the 1 proton by itself. It doesn't actually need neutrons to hold it together, so it, for the most part, doesn't. So that's protium, like 98% of the hydrogen out there, maybe 99%. Then you have deuterium, 1 proton and 1 neutron. That's like most of the remaining hydrogen in the universe. And then you have tritium, 1 proton and 2 neutrons. Okay? They're vanishingly small. But almost all elements have these different isotopes. And going back to the periodic table, those different isotopes are the reason why you have these weird masses for the elements. So a lot of the magnesium out there has a mass of 24. Some has a mass of 26. And then the average between those two is 24.305. Iron has like 4 naturally occurring isotopes, and the average between those different isotopes comes out to 55.845. The overwhelming majority of the oxygen out there is oxygen 16. Thus, its mass is almost, but not quite, 16, and so on. So, now let's look at the symbology of elements. Every element is represented by a symbol, an abbreviation. It is always one capital letter or a capital letter and a lowercase letter. So, for example, hydrogen, carbon, fluorine. Those are just represented by the capital letters H, C, and F. Iron is represented, however, by Fe, sodium by Na, xenon by Xe. Now, these symbols are going to be surrounded by numbers. Sometimes. So, the lower left is where we put the atomic number. The atomic number Z is the number of protons. Okay. So, going back to our periodic table, Z for hydrogen would be 1. Z for beryllium would be 4. Okay, the number in the periodic table is the number of protons. Okay. It is the same for every atom of an element, and therefore it is often not included. It's redundant. If you're talking about helium, you know you're talking about an atom with 2 protons. Why bother to restate it? It's like saying, we have sent a probe to Mars, the 4th planet from the sun, the red planet. named after the war god Mars. You just keep on piling on redundant information. It's not particularly helpful. So we usually don't include the atomic number. In the upper left, we put the mass number. Now, I want to stress, the mass number is not the atomic mass. Okay? The atomic mass is the measured mass, the average mass in atomic mass units. Okay? The mass number is an actual counting of the total number of protons and neutrons. Okay? So every isotope is going to have a different mass number. So protium, going back, protium would have a mass number of 1. 1 plus 0 is 1. Deuterium would have a mass number of 2. 1 plus 1 is 2. Tritium has a mass number of 3. Okay? But they're going to have very different atomic masses. The atomic mass of protium is going to be about 1.00 or 1.007276. Okay? The atomic mass of deuterium would be that plus that, the proton plus the neutron. Right? So it's going to be slightly different for every isotope. Mass number, just the counting. It's going to be an actual whole number. Atomic mass is different. Okay. In the upper right, represented by the lowercase q, we have the charge of the atom. And this changes all the time. The atomic number Z will not change for a particular atom. The mass number A, unless you're doing nuclear chemistry, is not going to change. But charge changes all the time. Electrons are always flipping on and off atoms all over the place. That is the vast majority of chemistry. Excuse me. Drying up a bit. All right. So for that reason, charge is always included, unless it's 0. If it's 0, then we just leave it blank. Okay. But because charge changes all the time and it changes dramatically the behavior of the atom when it does change, we always have to include it. And technically, if it's blank, then it's 0 and it's still being included. Okay, so it's always there. And if you're looking for the way to calculate it based on the number of subatomic particles, charge is equal to the number of protons minus the number of electrons. Okay? So you lose electrons, you get a positive charge. You gain electrons, you get a negative charge, because electrons have a negative charge. Okay. So here are some examples, which in class we would work through, and I guess we can go ahead and do that next time I see you. You can go ahead and try those out yourself. Remember, lower left, we have the atomic number. Upper left, we have the mass number. And upper right, we have the charge. And then underneath each one of these elements, I've also included some extra information or extra blanks. So you have enough information to find and fill in all the blanks for these 6 elements. All right, so symbology. It's tough writing subscripts and superscripts on a computer. On a typewriter, it was a real pain in the ass. You actually had to move the sheet up and down, and then you would end up with your text looking all wonky because you never could get it lined back up correctly, and it just looked bad. So back in the day, they developed another way of talking about this. So instead of using subscripts and superscripts, they used something like this. C14, C-14 is referencing carbon 14, meaning carbon, which has an atomic number of 6, with a mass number of 14. That is to say, the isotope of carbon with 8 neutrons. So 6 plus 8 is 14. That is the kind of carbon used in carbon dating, radiometric dating, when they find stuff that's like 5 to 500,000 years old. Organic materials that are 5 to 500,000 years old. Similarly, iron 56 means iron with 30 neutrons. Or uranium 238. Uranium has an atomic number of 92, a mass number of 238. Therefore, 238 minus 92, we're looking at uranium with 146 neutrons. That's the nuclear bomb kind of uranium. So that is just a quick way of doing the same sort of thing. So when it does matter, when you are talking about a particular isotope, this is a very common way of talking about it, either C14 or carbon-14, iron-56, something like that. So, why do we do it all this way? Why do we have, the subscripts and superscripts and things like that? There might be reasons. More likely than not, it's just the way one of those dead white guys first started writing it down in their notebook, and we've never been able to get rid of it since because those things are just difficult to change. We start doing it a certain way, and we're stuck doing it that way forever. All right, and that is that for atomic structure and atomic symbology. Next time I see you, we'll go over these things.